Hello friends, I am Zeki. Today I will present the topic of assembly language. In this presentation, my aim is actually to explain assembly language not just a programming language, but as a fundamental bridge between hardware and software. And I'm going to mention about its relationship with the machine language, the role of assemblers, instructions, formats, processor registers, and execution flow. By the end, the main goal is to clearly understand why assembly language still matters in computer architecture. Assembly language can be described as one step above machine language. While machine language is written entirely in binary, assembly language uses symbolic instructions that are easier for humans to read, yet still very close to hardware. One important characteristic of assembly language is the use of mnemonics. These are short, meaningful names that represent machine instructions. Although assembly looks more readable than machine language, each mnemonic still maps almost directly to a single machine instruction, which means there is very little abstraction here. In this example, I tried to demonstrate how a simple high-level statement such as E equals A plus 4 is implemented in assembly language. The first value of A is loaded into A register, then an arithmetic operation is performed, and finally, the result is written back to memory. This clearly shows how assembly exposes the exact steps performed by the processor. Now I will talk about machine language. I will talk about differences between machine language and assembly language. Machine language is the native language of the processor and it's executed directly by hardware. It consists entirely of binary codes. On the other hand, assembly language represents the same instructions symbolically. While it's easier to read, it does not hide the hardware details, which makes it more powerful, but also more complex to use. Assemblers translate assembly code into the machine code, whereas compilers translate high-level languages into machine code either directly or via assembly. This explains where assembly fits in the translation process. The instruction set architecture defines the instructions, memory model, and registers visible to the programmer. The instruction sets also represents the interface between software and hardware. And it includes instruction set, memory, and programmer accessible registers. Mnemonics are symbolic representations of machine opcodes. For example, move represents a data transfer operation, which the assembler later converts into binary. Understanding assembly requires understanding processor organization. The 8086 processor is used here as a reference to explain registers and execution behavior. The 8086 processor contains general purpose registers such as AX, BX, GX, and DX, which are used for arithmetic operations, data movement, and control. Segment registers define the memory segments, while the flag register stores status information such as 0, carry, or overflow, which are used for conditional execution. An assembly instruction may include a label, an operation, operands, and a command. This flexible structure improves clarity and control. It doesn't mean that all these instruction types will be on our instruction field, but this is the main structure of an assembly instruction. Now I will talk about the all fields, and I will begin with label field. Labels are symbolic names used for instruction addresses, procedures, and variables. They improve readability, and they are translated by the assembler into actual memory addresses. Here are some examples of valid and invalid names in assembly language. Following naming rules is important to avoid assembler errors. The operation field specifies the symbolic opcode, such as move, add, or sub. It may also include assembler directives, which guide the assembler rather than generating machine code. The operation field, operand field, specifies the data to be processed. Depending on the instruction, there may be 0, 1, or 2 operands. The commands begin with a semicolon and they are ignored by the assembler. The good commands explain the purpose of the code rather than stating the obvious. Now I will talk about instruction types. Data transfer instructions transfer information between registers and memory locations or the ports. And there are some example instruction types under the explanation, as you see. And the other instruction types are arithmetic instructions. They perform arithmetic operations on binary or binary coded decimal numbers, like add, sub, inc, dec, and etc. And bit manipulation instructions perform shift, rotate, and logical operations on memory locations and registers. Control transfer instructions control sequence of the program execution, include jumps, procedure, and procedure transfers. And string instructions move, compare, and scan strings of information. As examples, moves, moves B, moves W, CMPC, and etc. And interrupt instructions. These types of instructions interrupt processor to service specific condition. The processor control instructions set the clear status flags and change the processor execution state. And lastly, miscellaneous instructions there are. And these are nope, wait, we can give examples on this instruction type. An assembler converts assembly source code into object files containing machine language. Assembly programming requires a toolchain including editors, assemblers, linkers, and debuggers, and each serving a specific role. Common examples include NASM and TASM, as you see on the slide. And this slide contrasts completion and assembly. Compilers manage high-level abstractions, while assemblers perform direct instruction translation. Assembly programming requires a toolchain including editors, assemblers, linkers, and debuggers, each serving a specific role, as I mentioned the last slide. And this is the graphical explanation of that explanation. And now I want to talk about linking and loading. The loading is the process of copying an executable image into memory. The more sophisticated loaders are able to relocate image to fit into available memory, and they must read just branch targets, load, and store addresses. On the other hand, linking is the process of resolving symbols between independent object files. And linkers, suppose we define a symbol in one module and want to use it another. And some notations such as .external is used to tell assembler that a symbol is defined in the another module. And linker will search symbol tables of other modules to resolve symbols and complete code generation before loading. And now the question, why assembly language? Assembly language provides direct hardware access and it's essential for system software, embedded systems, and performance critical code. And it provides us faster and shorter programs. The compilers do not always generate optimum code. The instruction set is important for machine designers. Compiler writers must be familiar with details of machine language. The assembly language helps us understand how software interacts with the processor, memory, and operating system at a low level. It shows how program interfaces with all the parts of a computer systems, and it shows how data is represented and stored in memory and on external devices, and it clarifies how processor accesses and executes instructions and how instructions access the process data. Yes, friends, I tried to tell you about assembly language basics. I hope you enjoyed the slides. It's the end of my presentation. Thank you all. Have a good day.